We should review where we are in this project. What we've shown so far is that if we can prove something from the axioms of PA+, then we have a deduction in Z infinity which is bounded, in the sense that it has bounds alpha b, where the ordinal alpha is less than epsilon 0. The counterpoint to this needs to be that we can't deduce Goodstein's theorem. It's not at all clear how you'd prove something like that. How would you prove that you can't deduce something? And that's actually pretty hard. What we do is define an even nicer kind of deduction and show that we can't deduce Goodstein's theorem using this nicer deduction. We're going to pick on the cut rule. A deduction in Z infinity is called cut-free if it doesn't use the cut rule. There are no steps anywhere in the deduction justified using the cut rule. And what we notice is that if you read a proof upwards, starting at the conclusion and reading up towards the axioms, the cut rule is the only one that has something new in the premise that wasn't in the conclusion. For example, the AND introduction rule has phi and psi in the conclusion. It has phi in one of the premises and psi in the other. But everything that appears in the premises appeared in some form in the conclusion. The cut rule is the exception. The premises of the cut rule involve some totally new sentence phi that might have no obvious relationship to the sentences in the conclusion. So when we don't use the cut rule, our deductions are really limited. Let's make that a theorem. It is not the case that Z infinity deduces for all x there exists a y, gy of x equals 0, with bound alpha k, where alpha is less than epsilon 0, and the deduction is cut-free. For all x there is a y so that gy of x is 0 is exactly Goodstein's theorem. For each x, after y steps, the Goodstein sequence starting with x reaches 0. The way we prove this is by analyzing what a cut-free deduction would have to look like. The simplest possible deduction would be to just deduce this for all x using for all introduction. So the previous steps are deductions of there is a y so that gy of n is 0 for each n, and then the simplest way to deduce that would be using exists introduction. So we should have gm of n equals 0 for some m, and gm of n is atomic, so in this hypothetical, this had better be a true atomic sentence. And the idea is that our bounds won't allow this. We need m to be at most h alpha of n, so when n is sufficiently big, this won't be a valid bounded deduction. This is what the rules for bounds in the exists introduction rule were designed to do. The full proof follows basically this idea. The complication is that we could mix nonsense like contraction and weakening in to hide this basic structure. So we can't guarantee that this ultimately counterfactual deduction looks quite as simple as the simplest possible version. So we abstract a little to get the right inductive hypothesis. If we have a cut-free deduction of Goodstein's theorem, every step in this deduction has to be a set of sentences, each of which appeared in the conclusion. So they have to be either the conclusion, for all x exists a y, gy of x equals 0, exists a y, gy of n equals 0 for some n, or gt of n equals 0 for some term t. Because there are no cuts, every sentence in every step must be contained somewhere in the conclusion. This working backwards from the conclusion becomes our induction. We go by induction on the ordinal bound alpha, since if we deduce something with bound alpha, all the premises must have a bound less than alpha. So our inductive condition is to show, by induction on the ordinal alpha, that we cannot deduce any set of sentences gamma with bounds alpha comma k, such that each sentence in gamma is either Goodstein's theorem, or there exists a y, gy of n equals 0 for an n at less than or equal to k, with g of n greater than h alpha of k, or gt of n equals 0 for a closed term t whose value is less than g of n. We suppose that this holds for every beta less than alpha, and we'll prove it for alpha. So suppose we had a set of sentences like this that we could deduce with bounds alpha k, and we'll show that this can't happen, that the only way to deduce this would be to violate the inductive hypothesis. This deduction must be justified by one of the rules. This can't be the true rule. The only atomic formulas in gamma are gt of n is equals 0, where t is less than g of n, where t is not as large as the number of steps you need for the Goodstein sequence starting with n. So gt of n is not 0, so this is a false atomic sentence because t is too small. The justification can't be weakening. If it were weakening, the premise would be a set delta, which is a subset of gamma. The bound beta would be less than alpha, tau of beta would be at most k, so in particular h beta of k would be less than h alpha of k. So delta is exactly the kind of set of sentences that the inductive hypothesis applies to. We've already assumed that we can't deduce delta with bounds beta comma k. Contraction has the same problem. If we justified gamma using contraction, we would have to have a deduction of gamma comma phi with bound beta k, where phi is one of the sentences already in gamma, so the inductive hypothesis would apply to gamma comma phi. The justification can't be and or introduction because there are no and or sentences in gamma. The justification can't be exists introduction. If it were, that would mean we would have one of these exists a y, g a y of n equals 0 in gamma. So the premises in the other sentences in gamma, let's call that gamma 0, together with gt of n, and t must be less than h alpha of k by the rules for bounds on exists introduction. But we promised that h alpha of k was less than g of n, so we would have to deduce the premise gamma prime gt of n with bounds beta comma k, where beta is too small and simple for this to work. Again, the inductive hypothesis tells us this can't happen. There are no cuts. The only rule left is for all introduction. Gamma could be a set gamma prime together with Goodstein's theorem. We would need a deduction of gamma prime together with exists a y, gy of n equals 0, with bounds beta n, comma, the larger of k and n for every n. For small values of n, that might be deducible, but the Goodstein function grows faster than h alpha of n. So as long as we pick a big enough n, g of n will be larger than h alpha of n, which will be larger than h beta n of n. So again, the inductive hypothesis tells us that some of these premises can't be deduced. So we can't give a cut-free, bounded proof of Goodstein's theorem. If we could prove Goodstein's theorem from PA+, we could give a bounded deduction, so what's left is to bridge the gap between bounded deductions and cut-free bounded deductions.